Welcome to the EU Energy Projects podcast, a podcast series from Enlit and friends, focusing on the clean energy transition for the European Union and the EU Commission-funded energy projects that will help us achieve it. My name is Areti Ntaradimou. I am the editor of the EU Energy Projects podcast and your host. Hello, everyone. Today's episode brings us to the heart of the EU's ambition to modernize and decarbonize its electricity transmission system through the Horizon Europe project EasyDC-FOS. The European Commission has made it clear that achieving a climate-neutral economy by 2050 requires not only more renewable generation, but also smarter, more resilient and more efficient transmission infrastructure. EasyDC-FOS contributes directly to this goal by developing a new generation of high-voltage direct current cables with longer lifetimes, higher temperature tolerance, and integrated fiber optic monitoring for real-time fault detection and predictive maintenance. Together with Manuel Muñoz, project lead of EasyDC-FOS, we are going to discuss how this initiative fits into the EU's broader strategy for energy security, innovation, and decarbonization. Manuel, thank you very much for being here with me today. And let me start by asking you if you could please outline how EasyDC-FOS aligns with the European Commission's priorities for the Green Deal and Repower EU plan.
Yes, hello, good morning, and thank you for this interview and opportunity to expose our project. So basically, EasyDC-FOS is a project that has been structured, designed in the specific way to accomplish the main objectives set by the European Commission on decarbonization and on the ability to be able to implement renewable energy sources at scale and to transport and transfer all of that energy safely, efficiently across Europe. So basically, the project is aiming at changing the current state of technology in terms of not only how the grid is operated, so how to operate a grid for long distance energy transport at high voltages, but also in the implementation of longer distance routes with cables, except of lines, with DC technology instead of AC. So actually bringing over the advantages of direct current, which has lower energy losses, as you all know. High voltage DC in 525 kV has over 1,000 kilometers, half the energy loss than if you do it in alternative current. So meaning, for example, in 1,000 kilometers, you would have around 200 megawatts of less energy loss than you would have in an AC cable project. So it is actually... Yeah.
So go on.
Yeah, so it's actually redesigning a 525 kV cable system. This is performed by Nexans, implement a new insulation material so that the thickness of the insulation can also be reduced. So at the same time as we are increasing the capacity of the cable, we're also reducing the environmental impact from its manufacturing and also from its implementation on the field. And then we are also developing those technologies that for very long distances would enable the line to be monitored effectively without having to displace brigades to the field. So actually performing remote diagnosis in a digital way so that all of that field work that today is done on this type of projects can be avoided. And we can do those tasks by monitoring technologies such as the DTS, DES, or the new partial discharge systems that we are developing with the rest of the partners there. So AP Sensing, Lumiker, and Passimon. And then really, I would say the main differential of this project is that we are building the systems. It's not a question only of simulating and design. We're actually building the prototype systems. We are testing them according to standard norms in Nexans laboratory, in our laboratory, and in Passim's laboratory. And then we are moving forward with two reputed TSOs that have experience in this type of projects for shorter distances to be able to enable us to trial them in their assets so that we can actually demonstrate that this technology has been developed effectively.
Manuel, you mentioned how much more effective HVDC is compared to AC. So I wanted to ask you, especially for cross-border interconnections and offshore grids, which are the things that the Commission now is pushing for with its mandate. How does your project support this transition from vision to reality? Because we discuss a lot about interconnections between countries. We discuss a lot about offshore integration, renewable power integration to the grid. However, that requires some serious high voltage direct current technologies. So how does EasyDC-FOS help towards that direction?
So I would say, first of all, it is enhancing cable designs from 525 kV to be able to produce 14% more power with the same voltage. That is increasing the current rating. So that means we're going to be able to transport more power with this level of state-of-the-art cables, 525 kV. Second one is that we are planning to be able to monitor that corridor for a longer distance. Today, effective monitoring with remote diagnosis is more or less at the level of 50 to 100 kilometers. The project is aiming to go up to 250 kilometers of efficient remote diagnosis. Thirdly, is that for the first time we're implementing predictive algorithms. So all of the data that we're going to have available from the cable design, from the simulation of that cable being done with the best tool sets, and then testing it so that we can correlate simulations and models with real life test data, is going to train algorithms so that we can predict the behavior of those lines in terms of capacity, aging. If a fault or an event is going to occur, we can know ahead of time. And then if there is a fault, if there is an event, to be able to solve it with a 20% less time. So today, in a 50-kilometer route, to solve an incident, it's taking about 1 to 2 months. The project is aiming to be able to locate the fault, know exactly where it is, and solve it in 20% less time. So that means in 1 or 2 weeks.
Hello everyone, Areti here. I would like to personally invite you to discover the EU Project Zone at Enlit Europe 2025 in Bilbao. Our event takes place from the 18th to the 20th of November. Come say hi to me at the EU Project Zone. Can we stay a little bit on this and could you tell me what other specific bottlenecks in HVDC cable technology is your project EasyDC-FOS addressing, and how will its outcomes help overcome current limitations in European transmission networks?
HVDC, I would say main challenges that we have for the project would be, the first one is the impact that XLP has, the environmental impact. So if you want to go higher in power and in power loads on the actual designs, you would have to move, for example, to have a 2 gigawatt capacity on a cable, you would be having to move beyond 525 kV, so probably to 700 and above kV to operate that asset safely. And this means that the thickness of the insulation is pretty high. So the need of XLP material on the insulation is high. And as we all know, XLP is a material coming from the oil and gas industry. So it's having an environmental impact. So it means that if we want to do this, there is a contradiction in that if we do it with higher powers, then yes, we are transporting renewable energy. So the aim is there, but we are using an asset that has a high impact in environmental impact. No? So first challenge is to have a very efficient XLP material which combines other chemical components so that at the level of 525 kV, we can already operate those cables at 2 gigawatts, which means 14% increase in power for that design level. Okay, so that's the first challenge that we're facing, or bottleneck that we're trying to solve. So reducing the environmental impact of the cable design. Second one is the cost of installation. So right now, cost of installation, if you want to go for very high loads to compensate and do the exchange between AC and DC in the power grid, you need very big valve stations. So the same thing happens here. If we can do it with lower voltage levels, so sticking to 525 kV voltage levels, the valve station to do the AC to DC conversion will be smaller, so also less costlier and then easier to build. Same happens, by the way, to the cable. If the cable is smaller and lighter, then when you are undergrounding it or doing the submarine works, it takes less time, and then it takes less space to trench, and it's also lower cost and lower lead times. Then you have the impact of faults. So today, to find a fault in an HVDC line is not easy. Short circuit levels in an HVDC line is around 2,000 amps, whereas compared to AC, it's 40,000 to 200,000 amps. So to see a short circuit in an AC cable, it's by short circuit is much easier because it has a very high amp short circuit level, whereas in a DC cable, this is happening at much lower amps, which means that to detect them, it's much more difficult. So we are building in new technologies that are able to track the acoustic wave, track the vibration of real faults, and actually have the knowledge through artificial intelligence and through testing to be able to detect faults in long distances. So as I mentioned before, also enhancing the distance range up to 250 kilometers to be able to see the complete circuit, not only a 50-kilometer part of the route. It's having a complete view of the cable system to 250 kilometers and be able to locate those faults. And then the other ones is right now to be able to know what the insulation health of an HVDC cable is, to be able to know what capacity, remaining capacity you have. Again, the monitoring solutions available in the market are going up to 50 kilometers, and they are not having any real algorithms. Aging actually is a new topic for HVDC cables. So how do you measure aging? Do you do it with the partial discharges as we're doing, or do you do it with another variable? If it's partial discharge, how can you have an early warning? Because we all know partial discharge up to the state of the art today is a late warning. So we are developing new methods to simulate partial discharges to much higher sensitivities. So going from the traditional 200 megahertz or even 10 megahertz that the state-of-the-art technology is doing today to 1 gigahertz. So we're able to see much more sensitive signals with the new sensors and having an earlier warning by tuning well the modelings that we're doing. So the finite element modelings that we're doing for the project in terms of space charge, how you can simulate that space charge, what that space charge is producing as an effect in partial discharges. So the project is having to solve all of these challenges that today the industry is facing.
And you also mentioned XLP insulation already, and I was wondering that in addition to smart monitoring tools, fiber optic sensing technologies, DTS, DAS, etc., that are part of the project, how they enhance operational safety and predictive maintenance for TSOs, for transmission system operators specifically.
Yes, I would say that there are like 3 different buckets to fill in. The first one is that today the industry in Europe and around the world, as you said, you have expert cable OEMs, expert cable monitoring companies, expert transmission system operators. But for the first time, I think this project is integrating all of these 3 lines. So the cable design is being simulated. That simulation is going to be correlated with real testing. That testing is going to be performed with the sensors designed for the project. Those sensors are the ones that are going to be later going to the field to see real operations. The complete monitoring system is integrated. So you have DTS, DAS, partial discharge, vibration, spot temperature sensing, all integrated into an edge node. Up to today, these are standalone systems. So it is the first time that really the industry is seeing this level of integration. So I think that's a first approach we are having to provide an integrated, comprehensive solution to the market from all of the 8 different elements. Second bucket, I think it's that, as I mentioned before, and I really want to stress this out, the project is building the things. We are manufacturing the sensors. We are manufacturing the cable. We are testing the cable in a real PQ test with 1.85 voltage rating out of the 525 kV. So this means that the testing is going to be done neatly at 800 kV levels. We are then moving to the field. We are putting all of these equipments to the real field and then having 2 real use cases, one a land cable and another one a submarine cable. So I think that for a first time, it's not a theoretical project. It's not an R&D project where you are seeing a model. It's moving from the design and finite element simulations all the way to real testing and real data. And this real data I think is the one, this is the third bucket, providing the main difference. With data, then you have the ability to train algorithms. You have to be able to the ability to be able to predict. Now, this is, I think, the three legs that we're having in the project that are, between all of them solving these challenges.
I will come back to real-time monitoring and data, but out of curiosity, where do you get raw materials from and how much do they cost you?
What type of raw materials?
Dealer's choice.
Raw materials, and this is something that, of course, in the project, we are bringing the objective that the industrial setup of Europe has to be independent, so that we can also be independent in our energy sources and energy transportation and use. But there is a reality still today that will also be a challenge for the future, and I think Europe is working on that fantastically. But the real raw materials of the mining materials, the copper, the insulating materials, or the microchips that we are having to buy for the project, or even some lasers for the monitoring systems. So very critical elements. Today, I would say about 40% is coming from European supply chains, but there is still around 60% that's coming from abroad, outside Europe.
Yeah, but still, that's a good number. I expected less from the EU. That makes me a little bit hopeful. Of course, I'll be extremely hopeful once the balance is changed and we have 60 from EU and 40 outside. But it is a really good start. Thanks for that optimistic mention.
Yes.
So going back to real time now and data, one of the project's key objectives is real time monitoring through an edge infrastructure, if I'm not mistaken. Now, how does this digital layer tie into the EU's broader goals about data spaces, digital sovereignty, and cyber resilience?
Yes, I mean, there is a new, in brackets, new standard. This is the IEC 62443 for data security. So everything that the project is delivering in terms of data management, so how the cables are behaving, how the transmission systems are being operated, is abiding to the standard. So all of the interrogators designs, the edge node itself is being designed to be abiding to that standard in origin. So from that first perspective, project is accomplishing that data security, that data governance according to the IEC standards. So I think it's giving a very credible approach to what Europe is really looking at, that data management is first accessible by the main parties providing services to the TSOs, which are important because they do have the knowledge of how the cable operates or how the monitoring systems are gathering the data. But it's also, so the complete ecosystem is built. It's not only that the TSO is having this data for itself, but it can also share it between the different parties. But it is safe and secured in the way that the parties that are sharing the data are doing it in a safe manner.
You mentioned some standardization, and I think that Horizon Europe projects often aim not only for technological development, although it is a very big chunk of their function, but also for knowledge sharing and standardization, which is a little bit of a painful topic within the European Union. How is EasyDC-FOS contributing to EU-wide standards for HVDC monitoring or insulation materials?
I would say that we are having most of the deliverables being shared to the European community. So there is a great deal of sharing the methods we're bringing. For example, aging. Aging is a complete new method that we are developing from scratch. So how are we using the partial discharges to be able to train our aging algorithms and combining this with other type of data such as temperature, vibrations, acoustics. So the project is having a big set of deliverables that are being published. So that's the first way to be able to standardize processes, designs, which is sharing how you're doing things. Second thing is, I would say most of the testings and results from tests that we will be doing when we are implementing the technology to the EnergyNet and the StarNet use case, this has a final deliverable that in terms of having to justify how we're meeting our objectives, would be shared as the results of the data that we have seen. So actually the results being monitored by the monitoring solutions of those real use cases. So I think this is also a good way of being able to standardize. So not only providing the methods and tools that how we are learning from them and what type of objectives we are reaching, but also actually sharing some of the results that the project will be gathering from the field tests. This is the second level. Now, third level is in the team we have real Congress figures. So next Monday, we'll be already sharing a tutorial in Gcable where we are sharing how the new methods, the new designs, the new installation materials are providing value to us. This is even happening at a very early stage in the project. So you see, even from an early stage, we're already doing big dissemination actions in good congresses such as the Gcable in Turin for HVDC cables. Then we have other gentlemen such as Joachim Iman from Energinet or Tony Lucinano from Statnet. And they have been promoting a new group in SIGRE, a new HVDC cable group in SIGRE that's meant to standardize aging methodologies. So aging methodologies for high voltage cable assets, not only for DC, but also for AC, where previously we have also done before the project a lot of work with them. So there we will be also disseminating methods, tools, and standardizing what are the correct equipments to do that type of monitoring. So we are having like a three-level approach to it. And I think we have this very nice 360-degree view that whatever we're doing, we are providing the evidences and the knowledge to the technical community. And then the SIGRE groups and the Gcable groups are having that knowledge to be able to develop from there and standardize from there.
Building on what you said on the three stages, you're also aiming to reach TRL5 through demonstrators in several countries, right? How does this pan-European testing environment reflect the Commission's objective of real-world validation for technologies critical to the energy transition? What you just mentioned with the consortium dissemination activities is, for example, one way.
Yes, I mean, if you see a real TRL5, which is a demonstration case, it can be in a simulated space and in real-time, real-world conditions. So in these terms, we are really overpassing this objective. The testing is not going to be done only in a simulated space where we are reproducing the complete environment, but we are going to the environment. We are really moving the designs, the monitoring systems, and the equipment to the real world. So I think the project has decided to take this step further and use part of the budget even beyond the objective of what the European Commission was having. So going to two real use cases. And we will be implementing the solutions in those use cases. So one is the Cobra cable in Denmark. The other one is a new land cable from Statnet. It's about 15 kilometers route. Once it's implemented, although for the project we are going to evaluate the first 6 months of results, those equipments will be staying there for more time. So actually, we can easily move from this 5 to ERL 7 or 8 very easily because we are having this enabler. The systems will be staying there for longer, and we will be able to expand the action for the coming Horizon 20 or for other actions for the European Commission to use this for further developments.
What would you say are the main policy or regulatory challenges to large-scale HVDC adoption in Europe? Are there areas where EU or national frameworks and national rules and regulations play a very important role too, still need to evolve? What would you say?
I'm not an expert in regulation, so sorry, but what I sense by going to the type of congresses I'm going where there is a lot of talks being done on regulations. For me, there is a big challenge in Europe, not only for the HVDC market, but overall, which is how to have a common regulation. So we're not talking here only about the HVDC world. It's also about how you implement renewable energies, how you trade energy between regions, how you operate lines, what type of protocols, grid protocols you're having to operate the lines. So it's how you retribute the capex. It's done differently in all the countries in Europe. So Spain has its own regulations, and even inside Spain, because you have like 17 big regions, those regions can also have different regulations, sub-regulations. It's different to France, different to Germany, and so far and so on. So I think that, first of all, before we say what's the challenges of specific regulation, for me, the real challenge is how do we have a common policy common regulation so that the game is the same for all. Okay, and so that we can define the space where we want to move in a lean way, and everyone is understanding exactly how to move in this space. And this space has to be Europe. It cannot be a single country or nation. I think that would, for me, would be the first topic to solve if we really want to go through long distance HVDC corridors. Projects is focusing on cable, but obviously you also have lines. So if you want to go for 1,000-kilometer hybrid line in HVDC with aerial parts and underground parts that are going to be crossing different regions. If in one side, for example, you have one nation or one country, and in the other side you have another country, you can just imagine how difficult it can be for two different TSOs to manage this if the regulations are completely different from both sides of the stream. No, so I would say that we should go for trans-regional transmission. Then there should be a very, I would say, homogeneous policy legislation from European level all the way down to regional level that is the same for everyone. That for me would be the solution or the enabler to really move forward with big projects and enabling this interconnection capacity. And by the way, we need this capacity, this interconnection capacity. For example, we had a recent outage in Spain, and part of the issue could have been solved if we had, now we're having 3 to 4% interconnections. If we have had 15 to 16% interconnections, such as, by the way, Denmark is interconnected much bigger way than we are, then maybe part of the problem could have been solved. So we have the need. Now also we have to really have a homogeneous approach to how we manage our grid.
Absolutely. For someone that's not focusing very much into rules and regulations, I would say you were spot on with what you said. We need a common denominator, even if it is difficult, because the various countries are in various, let's say, progression stages. But yes, I'm sure that the Commission will work towards that goal. It would make sense. And how do you see the role of Horizon Europe projects like EasyDC-FOS in shaping the next generation of European industrial leadership, especially in the context of strategic autonomy for key technologies, which is a very important topic, and we are a little bit behind from our competition, let's say, maybe.
Yes, I mean, I think they are a must to have to be able to integrate the knowledge that Europe is having at different levels. So from micro companies to SMEs, bigger companies, there is a lot of knowledge that if we combine together and we integrate, we can really produce new developments, new designs, and really solve these challenges that we were mentioning before. The only way to do it is through an integrated ecosystem, and this is where the European CL5 and specifically the Horizon 2020 action stands. So it's fantastic the way it drives this inter-community integration with big companies, small companies from regions across all of Europe. And then it also removes a lot of the burden of real R&D work. Now at Lumiker, we were constituted in the year 2009. We have been a very R&D company. And when you do R&D, when you are really developing and researching at scientific levels and then moving to higher TRLs, you never know how much it takes to reach the solution because you don't know if it's going to take one shot or 3 shots or 5 shots. Now with the Horizon 2020 Europe, what you know is that you have a budget that you can manage. So you have a stable base, stable foundation that will allow you not to do this trial and error, focus in a given pathway and really go for the results in that pathway. So I think it's really important, and we should be having more budget and more actions in Horizon 2020 if we really want to go for the solution of our, I would say, pain points more related to technology and to new products and methodologies to develop and operate our grids.
Amen to that, Manuel. As we're approaching the end of our discussion, I would like to close our conversation with a message. So I would like you to deliver a message, let's say, if you could deliver a message to decision makers in Brussels that are listening to this podcast about what's needed to accelerate the deployment of smart HVDC systems, what would it be?
So I would say that as part of our strategy to achieve climate neutrality, to upgrade our electricity power grids, and to build our industry, our internal industry in Europe, we should be homogenizing the regulation processes and working more as a integrated team between the different nations in Europe, seeing what Europe is and leaving behind our, I would say, more national objectives, because it is the know-how from all of the parts of Europe. It is the need from the different regions in Europe that will really make us develop and achieve our objectives, such as we're doing with the EasyDC-FOS project.
Thank you very much, Manuel, for this interesting conversation.
Thank you to you, Areti, and I'll be happy to answer any questions you have after or do any adjustments. Thank you very much.
I hope to see you at Enlit Europe, right, in Bilbao.
Yes, I will be there. Actually, it's going to be a fantastic opportunity because we are bringing the advisory board for the project, which contains also other TSOs and universities and really knowledgeable companies that we have in the advisory board. And then we're also doing our general assembly for the project. So we're taking the chance that we're all going to be there to do this very important action for us.
Amazing. I'll make sure to add all the relevant information for our listeners at the article that will accompany this episode. Thank you, Manuel.
Thank you very much. See you soon.
You've been listening to the EU Energy Projects podcast, a podcast brought to you by Enlit and Friends. You can find us on Spotify, Apple, and the Enlit World website. Just hit subscribe, and you can access our other episodes too. I'm Areti Ntaradimou. Thank you for joining us.